Hi, I'm Klaartje De Weerdt, and I'm a professor at the Norwegian University of Science and Technology in Trondheim, Norway. And for today's ROC&TOK, I'll be talking about chloride ingress in concrete. So, Norway has the second longest coastline in the world, about 100,000 kilometers of coastline, if we include all the islands, which means that a lot of our infrastructure is out there in the marine environment, such as, for example, this bridge at Lofoten. So then Norwegian bridge owners, such as the Norwegian Public Road Administration, are very concerned about the service life of their structures. They're beautiful structures and they should last as long as they are planned to. And one of the things that poses a threat to this service life is chloride-induced reinforcement corrosion. So when chlorides penetrate the concrete cover and they reach sufficiently high concentration at the reinforcement and cause corrosion. So owners like the Norwegian Public Road Administration want to make sure that the concrete cover is protecting the reinforcement sufficiently, guaranteeing a service life. So they've been very proactive on this, and they have, since the 90s, established field exposure sites along the Norwegian coast. So this is an example of one of them. This is the exposure site at Solsvik, near Bergen. And you can see they're exposing different concrete beams here with different concrete compositions or different binders to a marine environment to harvest long-term exposed data under slight controlled conditions. This is one example of an exposure site. And another example is here. This is one which was a bit closer to our university at the Trondheim Fjord, but that one was sadly closed down in 2013, 2014. There we had some wall elements exposed in the tidal zone of the Trondheim Fjord. Now, this was actually the kickoff of my postdoc, and it was one of the first things I was doing looking into concrete durability in marine environment. Because before this, I did my master's in civil engineering, and I did a PhD looking into novel cements and cement hydration. But I actually quickly figured out that it makes no sense to just develop a cement. It also needs to be durable. So I got more and more interested in durability and decided then to do a postdoc together with Professor Mette Geker on concrete durability in marine environment. And having done a PhD on cement hydration, I had learned a lot of tools to look at hydration phases in cement paste. So I used TGA, XRD, so thermogrammetric analysis, X-ray diffraction, ICP-MS to look at solutions, and scanning electron microscopy to look at microstructure and phase changes. So I used this toolbox I had learned from cement hydration studies on these marine exposed samples. And the sketch on this side, there you can see how I did it. I profile ground. So first we drill the core of these wall elements or beam elements, then we profile ground it to get powder at different depths from the exposed surface, which we analyzed with a range of techniques. And we always made some polished sections to look at the microstructure using scanning electron microscopy. So in this talk today, I'll tell you about the experience we have from field exposure, but I'll also be talking about how this triggered us to do a range of laboratory experiments, which I did first during my postdoc, but then later on together with PhD students and postdocs. So this will be how we try to understand chloride profiles a bit better, because they're actually a very important tool for engineers that are looking at maintenance of our reinforced concrete infrastructure. So join me on this journey. So we started by looking at these field exposed samples. So on the map above here, you can see number 7 was where we had these beams hanging from a ferry dock. That's that exposure site. And number 8 above there, that's the exposure site close to our university and the Trondheim Fjord. So we harvested some data from those, but in order to be sure that these are generally applicable data, I collaborated with Ola Hjort Jacobsen, who's a researcher from Denmark, and she had been collecting similar data from Danish field exposure sites. They have slightly different temperature, it's a bit more south, a bit warmer, and they have different salinity. So that was actually quite interesting. Are the findings we have from our Norwegian field exposure site how general are they? And we can actually see that we have the same elemental zonation. And the following figure illustrates, it's just a selection of concretes we've looked at, illustrate how general this elemental zonation is. So just about, there's this long names for the samples. The first part refers to the binder, so we had different cement compositions. The second part is the location, so these are from different locations in Norway and Denmark. And also we had different exposure times. So some were exposed for only 10 years, whereas others were exposed for up to 75 years. And everywhere we could see these blue bar illustrating the magnesium-enriched zone at the surface. In some cases, there was also some sodium in this zone. These zones are then followed by the yellow zone, marking the sulfur-enriched zone. And then deeper, and we find a chloride-enriched zone, illustrated here with red, pinkish color. So it's very clear in this graph, but note that the horizontal axis is in a logarithmic scale. So we're really zooming into what is happening on the surface. If we change this into a linear scale, you can see that this magnesium and sulfur-enriched zone is relatively narrow. So the chloride-enriched zone is the one reaching the deepest. But at the surface, we systematically have the magnesium-enriched zone, sulfur-enriched zone, and then the chlorides. So just to illustrate it on how we detect these zones, I have one example here. It's from the field exposure site where we had these beams hanging from the ferry dock. And these are elemental profiles, which I determined with the scanning electron microscope and EDS. And we see at the surface, so the most left here on this figure, we have this blue band where I've marked magnesium. So you can see that the blue curve is highest there. So we have a magnesium enrichment in that zone. And sulfur, which is marked with yellow, and chloride, which is marked with red, is really low in that zone. So at the surface, magnesium is high, sulfur and chloride are low. When we move slightly deeper in, we have a small sulfur peak. So we get a sulfur enrichment slightly deeper in. And then if we move even further deeper in, then we see that the red curve, the chloride curve, is going up, and we get the chloride enrichment. Again, marked at the beginning of the horizontal axis is in a logarithmic scale, so we're really zooming into what happens on the surface, whereas the second part is a linear scale. And there I'm matching the EDS profiles with profiles I have from titration. So the traditional way of looking at chloride profiles is by chloride titration. And you can also see there a decrease in the Portlandite profile, the green profile, so showing that there's leaching in these samples. So we're losing Portlandite towards the surface. So just for clarity, I once more add the same graph where the axis is totally linear, and then you see that the sulfur and magnesium changes are very, very close to the surface. Now, I wanted also to show this picture or these figures because they showed or they illustrate some of the research questions that surfaced when looking at these field data. And one thing is, if we systematically see this magnesium and sulfur-rich zone at the surface, how do these two zones affect the chloride ingress? Are they tightening our system? Are they limiting it? So what is their role in chloride ingress? And the second question is that I want to draw your attention once more back to the graph on the left here, and to the blue zone where you have the magnesium enrichment. There, the chloride levels are really low. So at the surface, chloride levels in our concrete are low. We always learn that chlorides move from the higher concentration to the lower. So the surface concentration should be the potential for chloride ingress. But what we're seeing here is that at the surface, the chloride concentrations are lower than slightly deeper in. How does that match with chloride diffusion? What does that actually indicate? So I wanted to understand this better. Why are the chlorides at the surface actually rather low? So, as I normally do, if something doesn't really make sense, I try to simplify it and make a small experimental setup in the laboratory. Though this was not a small setup. I made a bunch of different mortar samples here, and I compared chloride ingress from seawater with chloride ingress from sodium chloride solution with a similar chloride concentration. So I have the same potential in my solution in a way, same chloride concentration, but in one it's just pure sodium chloride solution, and in the other one it's seawater. and seawater is rich in magnesium and sulfur. So by comparing these two, I can say something about the role of magnesium and sulfur on chloride ingress. This was real seawater. I got it from the Trondheim fjord. So, and you can see behind me, that's the setup. I just made lots of mortar samples and exposed them in different boxes and exchanged the exposure solution every week to simulate what would happen in seawater, like having an endless or almost endless reservoir in contact with my samples. As I mentioned, during my PhD, I looked into cement hydration, and there I learned to use thermodynamic modeling to predict the hydrate assemblage. And here I developed, together with Barbara Losenbach, a very simple model to look at the phase changes we could expect upon exposure to seawater and sodium chloride solution. So the figure at the left is for sodium chloride solution, and you have to read these figures as follows. So on where we have 1 on the horizontal axis, that's where we have a very small addition of the exposure solution to a hydrated cement paste. And so let's start with the sodium chloride. So if you look at 1 and above there, you see the hydrated assemblage of a hydrated cement paste with very little sodium chloride added. And what we're doing when we move in towards Origo is we're adding more and more sodium chloride solution. And what we can see that's changing in the case of sodium chloride solution is we go on the top, we have the monocarbonate, the purple phase, that's going over into the red phase, which is Friedel salt. So we're binding chlorides in Friedel salt. And the other thing we can see, because I'm not going into detail in all the phases, is that we see a general decline in the total volume of the phases formed. So when we're adding more and more sodium chloride, we are in a way leaching out solids after a while. We can clearly see that on the yellow phase, Portlandite, it's gradually dissolving when we're adding more and more sodium chloride. So the point most toward the left, so close to with a very high sodium chloride additions, simulates what we would expect at the exposed surface. And similarly, we can do it like this here for seawater. So at 1, it's very little seawater it is exposed to, so we have the normal hydrate assemblage, CSH, and so on. When we're adding more and more seawater, we again see that the purple phase, monocarbonate, is transforming to Friedel salt, to the red phase. And in addition, we can see this orange phase, attringite, is increasing in volume. And that is due to the sulfur in the seawater. We're getting more and more attringite. And that leads to a total increase of the volume of our hydration phases. So this could indicate a tightening of the pore structure, potentially. And if you add even more seawater to our system, we're forming a lot of these blue phases, which I've used to mark the magnesium-rich phases. It could be MSH, brucite, hydrotalcite. So these we are expecting to form at when we're in contact with a high volume of seawater, so at the surface. So let's now see how these predictions match our experimental results. So again, I used a bunch of techniques to look at the hydrate assemblage, but I'll focus on the findings we got from looking at polished sections in the scanning electron microscope and looking at elemental maps. So here they are, elemental maps, which I took from a polished section of a sample exposed for 90 days to sodium chloride solution in the top, and in the bottom here, for 90 days to seawater. And this is for a Portland cement. But in order to guide your eye, because this is a lot of information in one slide, I'm going to put some boxes around the maps I'm talking about. So let's start with sodium chloride exposure and look at the backscatter electron image. So the top of these images is the exposed surface. And we can see that on the top, it's actually getting it's getting slightly darker in the cement paste. So it looks like we might be losing material upon exposure to sodium chloride. And that matches with the calcium map, where we see that in the cement paste, which is rich in calcium, it's getting slightly darker at the top, so we're losing calcium in our cement paste. So we are most likely having some leaching. There's not that much to see in the aluminium, so I jump over that. If when we look at the silicon, this is a very nice illustration of what is sand. So the sand particles I've used are very rich in silicon. So these are the sand particles, else there's not that much to see. Also for the magnesium, there's not that much to see in the sodium chloride exposed sample. For chloride, the chloride map shows that we have chloride enrichment in the cement paste, so it's the negative of the silicon map, though there's less chloride in the top, so we have lower chloride levels at the surface. For the sodium, you can see that there's a sodium enrichment in the top of the cement paste. So at the surface, we have a slight sodium enrichment. And that might actually match if we look at the modeling on top here. I think it doesn't reach that part, but there you can see natural light. And the sodium might be an indication of zeolite precursors forming at the surface. For sulfur, then there's also not that much to see. So these findings from our elemental maps and our BSE image indicate that we have leaching towards the surface and we have chloride enrichment in the paste, which matches our model. So that was nice. But let's now look at the seawater. So if you look at the BSE image, we don't have this darkening of the cement paste towards the exposed surface. So we don't have the same extent of leaching or dissolution of our cement paste. On the top, we have some dark gray matter, and when we look at the elemental maps, we can see what this is. So when we look at calcium, we see that we have something drizzled on the surface. That's calcium carbonate forming at the surface. And also see a lot of calcium in the cement paste, but not really the clear leaching as we saw for sodium chloride. Jump over aluminium, not that interesting here. Silicon, again, a good illustration of what are the sand particles, which are rich in silicon. And then here we have the magnesium. That's quite interesting because we see like a carpet of magnesium on the surface. So this is brucite precipitation on the surface. We don't really see MSH yet, and we think that is because that takes some time to fall. But we do see a clear brucite enrichment. Then chloride enrichment in the cement paste, as expected. We don't really have a sodium enrichment in the cement paste. There's some sodium in the brucite precipitated layer, but not really in the cement paste. And interestingly, when we look at the sulfur, we actually see a sulfur enrichment in the paste. So we do get sulfur from the seawater in our cement paste. And that matches with this model. We do get enhanced Attringite formation towards the surface, more sulfur, and we have the precipitation of this one here, brucite, on our surface. So this very simple thermodynamic model actually predicts kind of what's going on in reality. Now, the question remains, does this magnesium and the sulfur actually affect our chloride ingress? And here's the answer. What we're seeing here is the chloride profiles for the seawater exposed and sodium chloride exposed sample. And we see that the seawater exposed sample has the highest chloride levels and a slightly higher, one could say deeper ingress compared to sodium chloride. So what this is showing is that actually if sulfur and magnesium would be reducing your chloride ingress, the seawater profile should be below the sodium chloride profile, but it isn't. So we can actually, based on these results, conclude that magnesium and sulfur do not limit the chloride ingress. The formation of the Attringite and the formation of the magnesium-rich phases do not actually clog the pores that are in which chloride is ingressing. So they are not really affecting the chloride ingress. They might affect leaching, but that's something we come back to later. So this one is out of the world. Magnesium and sulfur do not prevent chloride ingress. But we have still this other question remaining. How can we explain the low chloride concentrations we observed at the exposed surface? The ones I was puzzled about, they should be high because they are the force driving the chlorides into the concrete. So then we need to take one step back in order to understand that. I just want to illustrate the importance of chloride binding in these chloride profiles. So I took a chloride profile here from Solsvik, which was the exposure site with the beams hanging from the ferry dock. And this is a profile after 16 years. The binder composition is mentioned there. It contains a bit of fly ash and some silica fume. Now, I put this red circle there because I want to focus on the chloride concentration at a depth of 10 to 15 millimeters, because these are cast beams, which means that at the surface, we have a higher paste content. We call this the wall effect. You can't have coarse aggregates at where you have the formwork. So you have a higher paste content at the surface. And that makes it tricky because it's a paste as the part that's binding the chlorides. So I want to move a bit away from the surface and look at a part where we can assume that we have bulk composition of the concrete. So that's why I want to focus at the chloride ingress at about 10 to 50 millimeters. So if we look at the chloride content there, it's about 0.5 mass percent of dry concrete. So if we take this value, and I'm going to try to break it down to where can we find these chlorides. The first thing I do is on this concrete, on the bulk part of the concrete, we determine the suction porosity. We did it by drying in the oven and saturating it in water, and we obtained and weighing, looking at the weight difference, and we got a suction porosity of 15 volume%. And this is quite high because we dried at 105. So we killed some attringite and CSH on the way. But if we take this 15 volume% and we fill it with a chloride solution with the same concentration as the seawater, we would get about 0.1 weight% of concrete. So it's this what is marked in this graph here above, a porous solution. If we fill all porosity with a solution with the same chloride concentration as seawater, it would only represent 0.1 weight% of dry concrete. So it's only a small part which can be represented as free chlorides, as the one that is filling, if we fill all pores with seawater. So the remaining part has to be associated in one way or another with the solids. And in order to do so, I again used my thermodynamic model and I calculated what hydrate assemblage I would have, assuming a degree of reaction of 85% for my Portland cement, 30% for my fly ash, and all silica fume has reacted. And then I get this hydrate assemblage. And I assume that all my EFM is Friedel salt, and I used the ideal stoichiometry of Friedel salt. Then that would represent this amount of chlorides in my Friedel salt. So that would stand for almost 0.2 weight% of the chlorides in the section indicated with the red circle. And the remaining part I associate with the CSH. I determine the amount of CSH using thermodynamic modeling, and I also have some data from field exposed samples of how much chloride the CSH actually can contain. And this matches quite well. Though there's lots of assumptions here, so these levels can vary a bit, but it just illustrates. So if you look at a chloride profile, a large part of it is bound in either Friedel salt or absorbed on CSH, and only a small part is free in your pore solution. So chloride binding is extremely important if you want to understand chloride profiles. So that's why during my postdoc, I started playing around with chloride binding. And I used this setup where I put well-hydrated cement paste in contact with different chloride-containing solutions and checked how much chlorides can they actually take up, and also try to analyze the solids to see what phases do actually form. So the first and very simple setup I did was looking at the cation effect. So comparing chloride binding when exposed to sodium chloride with chloride binding when exposed to calcium or magnesium chloride. The graph I'm showing here shows you on the vertical axis the amount of bound chlorides, so how much chlorides can your cement paste take up, and on the horizontal axis it shows you the chloride concentration this cement paste is in equilibrium with. You can see that there's a very large difference between definitely when we look at chloride concentrations higher than 0.5 mole per liter between sodium chloride and calcium or magnesium chloride. We could actually link this to the changes in the pH in these solutions. So for sodium chloride, when we have a low concentration, we get a slight increase in our pH, and then it kind of levels out. Whereas for magnesium and calcium chloride, we have a considerable decrease in our pH when we're adding or when we're increasing the concentrations of these two salts. And when we plotted the pH as a function of the amount of bound chlorides, we could actually see a quite clear correlation between the two. So the lower the pH, the higher the chlorides, or the higher amount of chlorides that could be bound. So in order to dig a little bit deeper into this pH dependency, we did another setup. And what we did here, so we repeated the binding isotherms, and then we said, let's take a point on the sodium chloride binding isotherm, which is actually on a plateau. And let's add hydrochloric acid. The things we're doing then is we're adding more chloride, so we're moving further away along the horizontal axis, and we are changing the pH. That's the two things. We're not adding any other elements, we're changing pH and adding more chlorides. And our idea was, if we're changing the pH, should we move closer towards the calcium chloride curve? And how far would that go? And would we at a certain point have, again, a decrease in binding? And that's exactly what we observed. So we're going, when we are decreasing the pH by adding hydrochloric acid, we are first increasing the binding to a certain point, and then when we surpass a certain limit of pH, we're then again decreasing the chloride binding in our paste. But then we also wanted to link this to our binding phases in our cement paste. So what's the role of CSH? What's the role of AFM or Friedel salt in this? And this is work done by Peter Hemster during his master thesis and the beginning of his PhD, and together with Alisa Machner. What Peter did is he quantified the amount of chloride AFM using TGA, and he plotted this as function of the pH. And he also saw that the chloride content in the AFM changes with pH. So he also documented that using semi-DS. And when we combine these two, we can look at the impact of AFM. So we calculated the impact of AFM on this pH-dependent chloride binding of our Portland cement. What we can see is that the AFM follows this first increase with chloride binding when pH decreases to a certain level, and then it decreases again if the pH decreases even further. Though the AFM is not explaining the entire story, our hypothesis is that CSH has a similar behavior, though we were not able to prove that in this setup. So there's definitely work to be done here to actually demonstrate the pH dependency of chloride absorption in CSH. Now we've seen that chloride binding is pH dependent. So how does that relate to our research question? So where we were wondering, how can we explain these low chloride concentrations at the exposed surface? So I first need to say, most of the chlorides, or a large part of the chlorides in the chloride profile, are bound. So chloride binding will be explaining this, or will explain this. And so let's combine the figure here where we have pH-dependent chloride binding with the chloride profile we've been looking at earlier, showing this very low chloride concentration at the surface. So what we can see at the surface where we have this magnesium enrichment, we have a low pH, a pH towards 10. This means severe leaching, and when we have so severe leaching, our hydration phases are not able to take up or absorb any chlorides anymore, and we have a low total chloride content. Though when we move slightly deeper in, we have moderate leaching, and we actually have an enhanced chloride binding, explaining why we have these higher chloride levels slightly deeper in. And then if we move even further deeper in, our chloride binding is not as much affected by leaching anymore, and we come closer to chloride binding values which we would observe for sodium chloride. So we weren't fully satisfied yet, because now we saw that leaching has a major impact on chloride ingress. And together with Alisa Machner during her postdoc and as part of the Horizon 2020 Endocrine project, we took it a step further. And we exposed mortar samples with a novel cement, which was developed in this project, to two different exposure solutions. So on the left, we have 3% sodium chloride. And then we had the other exposure solution where we added potassium hydroxide. We added 150 millimole per liter to simulate a little bit the alkalinity level of the pore solution. Exposure solutions were exchanged weekly, but in one we had just sodium chloride, and in the other we had added additional potassium hydroxide to limit leaching. So let's look at the results. We start with Portlandite profiles, which are an indication of leaching. So we saw that's one of the solids that's actually dissolving first when you have leaching. So on the left, we have sodium chloride. At the horizontal axis, we can see that there's actually the Portlandite content starts to decrease from a value of about 10 millimeters in. That's for the sodium chloride exposure. If we look at this graph here, where we have added potassium hydroxide to limit leaching, but this is sodium chloride with potassium hydroxide to limit leaching, we can see that the Portlandite is actually on a background level, and it's only decreasing in the outer couple of millimeters. So we are able to limit leaching by adding potassium hydroxide. So now, what is the impact of these two different levels of leaching on chloride ingress? Here is the chloride ingress profile, and they are very different. If we look at the most leached samples, or the one exposed to sodium chloride, we have much higher chloride levels and further chloride ingress compared to the one here where we've added potassium hydroxide to limit leaching. So it really impacts our chloride profiles. And then Alisa linked these chloride profiles to the amount of phases which are able to interact with chlorides and their chloride content. And we were able to match these differences these chloride profiles by how much chloride is absorbed in the CSH, how much is taken up by the Friedel salt, and also a small portion in the pore solution. So here we really demonstrated how important leaching is when it comes to chloride ingress. So what? Let's round this up. Chloride profiles are largely reflect bound chlorides. And that's good, because actually bound chlorides are in a way an indicator of how far the chloride has reached. Imagine that our cement paste wouldn't bind chlorides. We wouldn't know how far they get. So binding in a way is a good indicator. Though we've also now seen that chloride binding is really affected by leaching. So both the chloride absorption in the CSH and the chloride in the EPFL is strongly affected by leaching. So the shape of the chloride profiles is strongly influenced by leaching. So if we're going to develop mechanistic models or engineering models, they have to account for this. So one example of how to deal with this is a model proposed by one of our former PhD students, Simon Fianbo, and he looked into the square root method to look at chloride ingress predictions. And what he does there, as illustrated in this first figure, is he discards the first part of the chloride profile, which is heavily affected by leaching. And he looks deeper into the chloride profiles, defines, as shown here in the second figure, a reference chloride content, and he determines the ingress depth for that reference chloride content on the chloride profile. And then he determines this depth for different exposure times. And when you then plot the ingress depth as a function of the square root of the exposure time, you get a linear function. So this is a very simple engineering model to predict chloride ingress over time. Though there's still a lot of work to be done to use this method in the design phase of reinforced concrete structures. Though it actually shows that relatively simple models can be extremely interesting and account for some phenomena which are very complex. So I want to thank you for your attention, but I have to say that this is not my work I've done on my own. I've done this together with a lot of people. Started my postdoc together with Mette, worked a lot together with Ola, Barbara Lotenbach, Harald Justnes, and so on. Lots of very nice colleagues at the Norwegian Public Road Administration and at the cement producer, and then none the least, all these wonderful students that joined me on this journey. So thanks to all of them. If you want to read up on more of this, please check our publications. So, thank you.